I get past that, I wanted to, if by that time, if we will not have progress to the gazebo, then I'll just take it up and move it to the gazebo so that we can also use the gazebo.
Okay.
And today is like, is there anyone who's going to present something, or is this like open for discussion and stuff?
Yeah, open for discussion. If you if you have an update, that'd be cool
I,
to see.
so I was, like last weekend, I was able to work a bit on the path tracker node. So it's almost like about 90% complete now. I was actually totally could not do it for various reasons since last 2 or 3 weeks. And at one point, Chinmay also pinged me, but I was like really not into that thing. It was really busy, and then I got a little bit the sick kind of a deal. So I could not respond to Chinmay because he's got some bandwidth available to work on the path planner, but that didn't actually happen because I had just had that one document. Anyways, the path, the tracker that I'm almost 90% complete, and my last 10% part is, and then I will be into the testing, and then we'll just probably hit some more blocks. But the last 10% where I need the input, where right now you got like two messages that I'm considering. The one's the twist, and the other one's the Ackerman. But our vehicle's Ackerman, so I got only two outputs. The ones for the velocity, like for the rear axle center point, and the ones for and one for the steering angle. So how I can turn it. So right now the path, the tracker would output these two sort of outputs. The ones like in Ackerman messages. So one's the speed and the other one's the angle for the vehicle. So I'm not sure if that would suffice, like for our use case. If I have these two outputs, would that be helpful in any way, or do we need something else besides like just the velocity and the turning angle?
The units on the twist message for the Angular Z, is that what are the units on that?
Radians per second.
Oh, radians per second.
Yep.
Okay, and then we can get that. So you can get curvature, and then curvature will get steer angle. So
Correct.
okay. So yeah, I think we at least we talked about on the robot side being able to receive a command velocity message. So if we had linear x velocity, and then we had the radians,
Yep.
and then we can create a node from the PID, from not PID, from the path planner to convert that to the radians.
You mean to say path tracker?
Path tracker, thank you.
Yeah.
Yep.
Okay.
So I have a quick question. Where do you measure? Do you measure from the center of the vehicle, or do you measure from the front of the vehicle to get the angle of the wheels?
Yeah, the front axle center, that's where our angle would lie. So it means that we have to compensate for both the steering link, basically. So we're measuring right at the center. So that would be the output. And then we'll have to tune it to make sure that, how it actually turns from left to right.
Yeah, okay. So you're measuring exactly halfway between the two front wheels.
That is correct, yes.
The focal point, wherever the steering point is on the right and the steering point on the left. Exactly in the middle of that.
Correct, yeah. So
Okay.
that's where we'll have the angle. And then based on that output, we'll just have to, depending on your vehicle, you would just tune it to, what's the angle that's appropriate for your steering link. You got that kingpin, and then you got that steering linkages, so if you have the center, even if you have the left wheel drive and then the steering on the left, you should be able to actually adjust the angles, because obviously when you make a turn or left turn, your one angle is just probably greater than the other one.
Right.
But I think it's automated.
Is
If
that
you
the
have
same,
the 4-bar linkage, yes.
is that the same point that the path planning algorithms follow? Is the center point in the front?
Right, so it will have the parameter called the wheelbase. So as long as we know the wheelbase, it will actually calculate the angle based on the wheelbase that you provide.
Okay.
So, Alan, I think you're asking the point on the vehicle that we want to put on the line.
Right. Right.
Just for an Ackerman vehicle, it's the center of the back axle, and then imagine straight down.
So the steering, it's front wheel steer or rear wheel steer?
Front wheel steer.
So you'll have to have some kind of an offset then. So if your path planning algorithm, you want to follow the line, is the center point on the rear axle, the steering angle will be at the front. So there'll be just an offset. I think Sam mentioned the wheelbase. So
Correct.
that would be your offset then. Yeah.
Yeah,
Okay.
so we measure the velocity, like all the power, like the velocity will be right at the center rear axle. That's where we measure the velocity, and the angle would be like sort of, the center front axle. So that will be the steering angle. That would be actually computed, and then will be in terms of the Ackerman messages.
Ask them. I won't ask too many questions.
Sorry, do you have any questions, or you okay?
No, I can just, it's the load that you're pulling. So depending on the load, could cause drift, and if you're on a side slope, different things like that. So you have to have some way to compensate for all those different factors as well.
Yes, that is correct. So for the computation purposes, you got the Cartesian plane, so it's like real flat XY. So we don't consider Z at this point. If your lens flat, you're in luck. If your lens not really flat, what it would do is like upon every the loop, each loop it will try to get to the point where it's supposed to go. So it means that you will have some drift spoof a little bit here and there, but eventually we'll try and go to because because your vehicle is localized. If you like go drift side to side, it will actually determine that, and it will just give you the position. So for the next loop, when we are actually trying to follow the path, for the next loop, it will correct the angle, which is what's the current angle of the vehicle would be, and then where the point the path, the point on the path should be. And then it will just measure that. So it will have a little difference here and there, but I think we're looping like about, let's say, in between 10 to 50 hertz. So it will be very fast calculation.
Yeah. Okay. So yeah.
So a couple of things that I wanted to also mention: the TF3 and the building of the TF3 and broadcasting the frames, and then converting the point, transforming it from one frame to the other. So we're adding 2 frames dynamically, and then that's where actually it took me a lot of time to digest the concept, understand it, and then apply it. So we're adding 2 frames, at least 1 frame dynamically. The second frame, I'm still considering that I can add it dynamically, but then I'm still considering that I might be able to do it like directly to the static transform. So the frame that I'm adding, the frame that I'm adding is the carrot frame, which is like the distance, the lookup distance frame that we're adding, so that we can visualize that where the frame is, that frame which we're constantly kind of chasing. And then the second frame that I wanted to add is the Ackerman frame, which is like right at the front. So you will have the wheelbase, and then we should be able to, to show that what's the current angle. It's kind of calculating, and then that's the angle that we'll put the frame on, and then we should be able to show that, okay, where, what's the angle is basically. So, I mean, there are two line of thoughts. So right now I have put it like added dynamically, but then I can also probably do the static transform and then just put the Ackerman right out the front into the vehicle, and then it should come from the URDF. So I got like two things going on. I think both way it should work. Whatever's easiest, I'll see that if whatever's easiest, I think we'll just should go with that. But I think it's a good idea to add the Ackerman into the URDF. But right now I have not decided 100% that what I wanted to do. Any thoughts on those?
If it's not changing, so if it's just a position on the vehicle, those are just do static transform.
We're looking at the yaw, so that we wanted to reflect because that would actually show the steering angle
of the tires.
Exactly.
Yeah.
Well,
the joint rotation.
Yeah, it will be right at the center, and it will show you your yaw would be moving. I mean, that's your the angle to Z. It just because it will show you the steering angle.
Yeah, so that's just like a joint position. So you're just showing a joint position. That's all defined in the URDF. Yep.
Yeah. But you see, if I do it to the URDF, then I have to actually control it through the joint state, and may have to control it through the ROS controller. But if I do it, add it dynamically, I should be able to control it probably within the node, the path tracking node. So I think there's some work there. But I think other than that, I should be able to start testing in coming weeks.
Okay, awesome. That's cool. And if there's pieces of work that you can break off or easily separate, you want someone to work on, then maybe we can post those out and see if there are some people that have some time to work on it.
The path planning, that's the second thing that I wanted to move on to. And as I said, like a few weeks before too, that's the area where I'm going to look for the help.
Okay.
Like I said, I'm also coaching and then getting one other person's ready. And so that the person's also is going to help me build the path planning node. But I think that's where a lot of work is actually.
Okay.
To plan the path, depending on the fill polygon. So that would be a lot of a lot of work. But once that's done, I think we will be set with two nodes, which is once the planner and once the tracker. And the tracker would use the Pure Pursuit, as we said. So the whole thing is based on the Pure Pursuit. The path planner would actually plan the path for the whole field.
Okay, awesome.
Cool. Yeah, that's the updates. Any questions? Oh, and I will take any questions on the TF3, or if you have any issues with the TF build. I'm feeling
better about those.
90% confident.
Awesome.
Yep.
I've been playing with TFs and nodes. I've been working on robot localization, and when I work on robot localization, I can't think about anything else. Like, that's the only thing that I have to think about because it's too, like, it takes up a lot of space. And it's been interesting. One note, like, if you can put all of your electronics into a nice little box, it makes it easier because then you can bring it inside and power it up and do testing on the bench. But
yep.
I've posted a link to this tutorial on robot localization, and one of the things in this document they talk about, maybe I can share the screen. You have to know, like, what format your IMU data is in, whether it's, I'll show that. So they talk about these terms like NED and ENU. Are you familiar with those?
Yep, I do. NED and ENU, they're both. We usually use ENU, which is our easting, northing, and off frame.
But then this is kind of the format that I was real grateful they put this in here. I made it too big. I'll show you the layman's term of NED. Okay. This is kind of the section that I like. So, like, if you take your device, you know which direction you pointed or mounted your IMU and how your box is mounted on your tractor. So you just take a look at the Z and make sure that the Z is plus. And then he says if you rotate it left side up, you should measure gravity on that side. And then if you pitch your nose down, you should read acceleration there. And this is a really quick, easy test because to tell if you have it mounted right and your data is coming in right. But real grateful that they put that in there in those terms. Yep. Because if I'm trying to do this and then I'm looking up diagrams and things are rotating around and then I got quantorians and I'm like, I have no idea. But he just says, take your IMU, point it down, and you should get 9.8. You take it, put it on your left, 9.8, And I'm like, sweet. So that was really helpful.
Yeah, that's pretty much what we need. Most of the IMUs, they measure like Z, like magnetic north. That's like 0 degrees. So in most cases, you have to convert that and offset it out to the east 0 degrees.
Yep. And I did find under diagnostics, the Razor IMU publishes the yaw angle. So that's a quick way to see that. But
well, yeah, if you're getting the heading, that's perfect. Yeah, just directly from the sensors.
Yep.
That actually makes your life a little bit easier.
So, and then the other error that I fixed today, which has taken me quite some time, on the NEMA serial driver that reads the serial port and takes in your GPS data. It's generally looking for a GGA message to do your lat long altitude. But if your GPS does output an RMC message, then that will give you heading. And so I turned that on, and then it ended up breaking robot localization. And it took some time to figure that out. So just a note. I posted those errors up into the lawn tractor channel.
Yep, that's all good lessons. If anyone's actually working on it and trying to make this work, at least on a physical vehicle, which I wanted to move on to, but I just wanted to finish all the software side of the parts first, and then I should move on to the build. Yeah,
the software part's a big part. You've got the simulator, so it's sitting there listening for a command velocity message, and it'll drive wherever you tell it to drive.
Yep, I wanted to convert that into the Ackerman, so I can do CMD eval right now. The twist messages can be done, but I think we just wanted to convert that into the Ackerman. So we'll see. So I'm not thinking about the twist messages at this point. I'm just thinking about the Ackerman messages.
Is there a reason? So if it's a little agnostic, if you use command velocity, if somebody happens to have a differential drive, then they can consume that. And if you have an Ackerman vehicle, you can consume a command velocity twist message and convert that to Ackerman on your vehicle. But that way it gives you the option, everybody can listen to the same message, and then if you have a variation on your vehicle side, you can make the change there.
So I believe we can do the twist too, but I think based on the use case, I have always considered the Ackerman. So I think we can do both. I mean, it's just the question of splitting it. You know, I don't want to use like one part from the one message type and the other from the other. So if we're having the twist, you know, you will have complete twist messages. That's for the differential vehicles, and then we will have the Ackerman messages. We'll convert that into the like sort of speed and the vehicle angle for the Ackerman messages. So you can do that. I mean, that can be done. But if you're like asking on we should do it like for the differential vehicle too, I think we can speed out these twist messages too, which is like be easier for the CMD well. Because essentially your twist messages, you know, where linear axis, the component that is not going to change is the linear axis. The components that's going to change, which is your angular z, you know, which is your angular velocity. What's just going to happen depending on, because you're measuring right at the center for differential vehicle, depending on what kind of turn that you're making, you know, you'll reduce the angular velocity component for the one wheel from the linear axis, and then you will increase on the other side, so it will just make a turn. So technically that's the only difference versus, you know, if you're doing the Ackerman, you know, I'll take the angular velocity component and try and convert that into an angle, and then try and reach that angle, you know, with the sort of the angular velocity, so that we can actually make changes to the steering. And we'll just need the feedback for that, obviously, because we don't know how much you're turning in terms of steering. And then Ackerman messages got velocity, also the acceleration, and also they have provision for the jerks. So I think we'll just do, if we have the angle, we'll just do the angular velocity and maybe acceleration a little bit. So you don't want to go, if you have the zero acceleration, you will try to go like one point to the other. It's like zoop, like that, you know. So you don't want to do that. You just want to slowly move it, probably, when you're actually turning the steering.
Those configurations are per vehicle.
Correct. You have to tune it then. Yep.
Mm-hmm. Those parameters go with every vehicle.
Correct. And then that's why I think we need to expose that on the outside, like where you can configure it. So it's probably the part of the parameters that you should be able to take care of it directly through the launch file.
Yep. We can do that. It's nice. ROS is really flexible. Lets you do those things.
Yep. So yes, it can be done. So I'll see that, you know, if whatever twist is easier, obviously. You know, based on the CMD well, and then it can be directly kind of consumed for the differential drive vehicles. I think Ackerman's a little bit harder, just because you have to actually take the component out and then convert that into, you know, your angle. It's not hard. It's like it probably would take time to get it right once you actually utilize that. And then moreover, your hardware side of the controller should be able to actually support that steering angle move, you know, based on the angle provided. So that's the other thing, you know. If hardware side of the controller, if it's not going to respond to it, be of no use. So I think there will be some kind of an interface challenges and issues that I kind of foresee at this point. Might not be, but I think we need a sort of controller which actually should be able to respond to the angles that we provide and calculate, and then should be able to move the vehicle slowly towards the desired angle. So it means that we'll have that feedback also coming in when we're moving the vehicle, and then it's just so that it goes so fast. If you're running it like, let's say, for 10 to 50 hertz, it will just go so fast in the loop that it will not have much time, you know, to just do something slowly. So I think you will have a little bit of jerky moments, but I think that's probably that's the part that probably you have to, like, it would be kind of custom tuning for each vehicle that you have to actually just play around and then see that on which, if you're comfortable, with some of the tunings and then that's the parameters right for your vehicle.
Yep. That's neat. That's pretty cool.
Yep.
Jeff, what's new in your world? You get your mic figured out?
Well, I was playing with one of the GPS receivers today, trying to figure out how accurate it was without correction data. And I see the new dual band one is somewhere between 0.5 meter to 2 meters, depending how long you let it sit there. And the old single band one was like twice as bad as that. So it was up to, at least 2 or 3 meters is all the more accurate that one would get. And the question came up, well, what if we don't have an expensive GPS that we're giving it correction data, that we either have to have extra hardware to get RTK, or we have to pay a lot of money to Novotel to get the TerraStar. And they say, well, what if we have a situation where we don't need to know exactly where we're at, like say in farming, you have to know your straight line down the field, but if you're just trying to drive around a track or something, or drive from here down to your farm down the road, you just got to stay on the road. So the question was, how accurate are the a non-corrected GPS? So that's what I played with today.
Have you seen people use DGPS or non-RTK in farming?
I was playing with my single band receiver. I turned that on. I turned on the S-Bass, and it was seeing the S-Bass satellites, and it seemed to get worse when I turned that on. So I don't know if I just didn't know what I was doing. And the new dual band one won't even let me turn it on, and I didn't dig through to see what I had to do to get that turned on. But if I turn on all 4 satellite constellations, so I had Beidou, which is the Chinese, I had Galileo, which is the European, then I had the American GPS and the Russian GLONASS. So I was tracking, it said it was tracking like 78 satellites and using something like 26 of those for the solution. And it was doing pretty good, considering that it's, I wasn't feeding in any correction data. And if I hadn't been on the company network, I could have clicked one button and sent it correction data, and then it would have dropped back down to 1 to 2 centimeters. But that wasn't the point I was trying to prove today. So that's kind of that's what I played with today. That's what I found out.
That's interesting. You can.
And these were both the U-Blocks receivers. It was the old M8T and the new F9P. And we also have some Swift Nav laying around, and we got the Novotel Smart 7 that I could do the same thing with. The reason this came up a few days ago, somebody in Denmark couldn't get the Novotel to work, and in posting one of the screenshots, it said the standard deviation was down to 1.34 meters, but it was not in the PPP mode, it was in the single point mode. And that's where somebody said, that's looking pretty good considering no correction data there. And the reason was, of course, one of our subscriptions had expired because they don't send us notifications because we have an under the table deal to get the things for free in the first place. So we didn't know that it had shut down on us. So anyway, that's why that all came up, because I thought, gee, if the modern dual band ones can get that good, how good can they get? Because we weren't even trying at that point. It was that's just a random screenshot they sent us to see what it, trying to find out what is wrong with this. And
so they're not. What's the difference between like precision and accuracy? Like they're stable position, but it's not accurate.
Yeah, and what I did was I just ignored all that, and I just did one of the screenshots. Let me see if I can. Here, I've got this computer in front of me. Let me pull one up here and see if I can find it.
I did some testing with this GPS, but it jumped around so much that it's almost unusable. It will tell you what state you're in.
Which GPS is it?
It's the BU353.
Okay, yeah, I've got one of those too. And I that's something I wanted to try too before I'm done here, but I forgot to take it to work today. let me pull up a screen here. Nah. I don't want that one. I want. Okay, let me see if I can share this. Let's see. Share. Let me try this and do here. Can I just do this directly? Okay, so if I say make this actual size, I don't know if you can read this or not, but this on the left that's my L1 just single band receiver running, and on the right is my dual band or multi-band receiver. And the biggest circle out here is a 2 meter diameter, and it's the same over here on the left. So you can see the most of the time it was within this 1 meter circle right there. So whether that's precision or accuracy, when I was watching it, it didn't go outside of that 1 meter, except for right here. It went out a little bit of the time. Now, if you'd slide this over, it would still fit within. You know, if I take the center of that, it would still fit within 1 meter. And then the one on the left, you can see here that it's not. You know, it's 2 or 3 times worse than the one over here on the right. And actually, I let it run for about an hour, and it was within this area right here. I was just ready to shut it down. I noticed that it started to wander out the top here. You can see my cursor, can't you?
Yes.
It started to wander out the top, just kind of slowly came up like this, wandered around here, and came back around here before I shut it down. It took like 10 minutes to do that. But I don't see any major jumps because John said, well, as long as it's not jumping, the EKF will probably take care of that. So I was kind of looking for it jumping. And the one over here on the left, it was basically in this big blob. And then when the other one started moving, this line came off the top and started wandering around up here. So it's interesting that one went out kind of to the left and one went out to the top. So, you know, between the 2 receivers, both from the same companies, that they're acting differently, which I guess that doesn't surprise me too much. And the other thing to note on this screen is these big columns here. These are the satellites. And I see at this time I had these top ones are Galileo, and then all the American flags are GPS, and the bottom ones are the Russian GLONASS. And at this point, I didn't have the Beidou turned on. And later, I guess, let me pull up that screen so I can find that. Here's one with. This is about, I'll probably go one too many here. One too many. There's my error trying to compile Yocto Linux that is a problem. So here you can see I ran this for about an hour and a half or so, and on the, I gotta make this big again. So here you can see the satellites is leaving trails behind, so you can see where the satellites were going through the sky. And then over here, this state again, this circle right here, the second circle is a 1 meter circle. And this time I had, you could see 4 of the Beidou satellites, and I was using 3 of those. And depending when I look at it, you know, some would come in, some would not. And down here it tells me, it says it's tracking 91 satellites, and it can see, it's actually using 25 of those satellites. And the other thing I noticed was this new receiver says it has a 60 channel receiver. In fact, this is right here on the screen. Down here it says it has 60 channels, whereas the old L1 only had 32 channels. So not only did they add the RTK into it and make a dual band, but now it's got 60 channels as opposed to 32 channels.
Wow.
So that's just some more fun facts I found out today playing with this stuff. So again, this is how it ran for about an hour and a half, and it started up here like this, and then just shortly afterwards it kind of wandered down here, and then just slowly wandered around over the rest of the time, and it's still within, you know, it's still within about a meter with the new receiver. So that may be good enough, to, you know, depending on what you're trying to do. If you're just trying to drive from the middle of your field back to the gate, and then once you get to the gate, you're either going to manually drive through or have cameras to get you through the gate, and it might even. You might even trust it to go through the gate. I don't know. But here, you're asking about the satellite corrections. Here's the SBAS, and if I turn this on, it for some reason it's got zeros in there to start with. I tried filling it in. It just one of them turned red. As soon as I'd say upload it to the thing, it just cleared it back out again. So I have to go dig through the documentation to see, because I'm sure I can turn that on somehow, and that may or may not give me a better better signal than what I got, but I assume it's not using the SBAS corrections at this point. And in America, it's the WAAS, which is Wide Area Augmentation System, is what they call their SBAS. And then what's the one? Galileo, the European one, they call it EGNOS, which I assume stands for European Geo Navigation something. I don't know what it stands for, but I can't see any way to turn that on, or I just don't know what it's called. Here's one called IMS that I don't know what it is, so it could be that's some kind of correction data too that I could pick up. And this IRNSS, I think, is part of the this Japanese thing for this QZSS, which is Quasi Zenith something. I don't know what that stands for either. But I can't see those satellites at all if I turn that on, because I think they just go over it's kind of a weird orbit where it goes over Japan and it goes over Australia. It just makes a big figure 8 over there, so I don't think we can ever see those satellites. So I was surprised I could get the Chinese satellites, but I can see right there, I could see 4 of them right there, and I could see more of them one other time when I was looking. If I back up here, you can see. But if you watch watch this pattern here on the side as I back up, you'll see it changing. So as I back up in time, you can see it's working its way back to this point, and then when I first started, it was now we're back into the other run that I did. So here, when I first started, it said it could see 6 of the Chinese satellites and a bunch of the Galileo, but if it's blue, it means I think the signal strength is low. If it's green, that means it's got a good signal and it's probably using it. And if it's red, it means it can't use those. So if you look on this chart here, see that the ones right along the edge are all red because they're too low on the horizon for it to honor those. So it just kicks them out completely. And then some of these are blue because they don't have high enough signal strength. And the other thing I should point out is this is a fairly expensive antenna that's mounted up on the roof. So if you put this on your robot with a cheaper antenna, it may not do this well either. So I don't know. And down here it says my Intrip client is not connected, and that's because on the company network they won't let me out with that IP address. So I have to get my home computer, or I have to get that one of those little Verizon hotspots like that one that Al has. If I plug that in, I can get out on cell phone data to get the correction data. So by doing that, you just click a button and it says, okay, you've got correction data. All of a sudden, bam, it just drops down to 1 to 2 centimeters over here and works just great. So I need to get it on something and put it outside and test all this stuff out to see how well this is working. So speaking of this particular receiver, Matt, have you played with yours anymore to know any better feel to how well this one's going to work?
Not yet. I've been playing with robot localization, but hopefully get a data set tomorrow.
Okay. Let's see, how do I do this? Stop share. Okay. So anyway, that's what I did today, and that's what's new in my world. And I didn't get anything done on my robot this weekend other than look at. I spray painted my whiteboard a couple more times, and that's about all I did on that. So that's kind of where I'm at.
That's neat. That's cool. Yeah, that GPS. I need to calibrate my my wheel encoders. So I haven't calibrated those yet. I was trying to get robot localization working so I could get my local coordinates from the GPS. So hopefully I can play around with that this week and get closer. I'd like to see how that you didn't get any those. It seemed your GPS seemed to drift, but it didn't seem to hop a lot.
I don't think I ever saw it actually jump. It actually would kind of just wander around and drift around. Now the older one, the L1 model, I noticed that one would occasionally jump. And I also noticed today when I was running it, it seemed just randomly you'd see the satellites would drop out. Just looking at the bars that scroll by, just all of a sudden a bunch of them were turned off for whatever reason. But I didn't notice that it was jumping, but yeah, like that first one you held up, that BU 353, those things do jump all over the place, and that one's old enough. That's L1 only, and it's GPS only, and it's just an old enough technology that's just what they did. So
okay. It looks really good. You have a really nice setup there testing those.
And that's just simply the software that comes with the the module, and then I just simply plugged it in the antenna on the roof and just sat there and let it run.
Well, looks promising. So keep going. Not
Okay.
as accurate, not as accurate as Al's. He's got centimeter level accuracy GPSs.
Well, if I just turn this one on, it would give me centimeter level. But that's not what we're trying to prove today. So I just don't know they'll give it to me all the time. That's the other thing. Another thing to keep in mind is, because the reason this whole thing came up is, well, you know, what if we don't have accurate GPS? You know, do we have to go back to our IMU and our wheel odometry, and can we rely on that? And say, what if, for instance, it's on your vehicle and you drive through a tunnel somewhere? You know, you drive through a big, long tunnel, and sure enough, your GPS is going to drop out completely. You won't have any signal from that. So then the next question is, how fast does it recover once you come out of the tunnel? And if you look at that guy's website, that RTK Live Explorer, he's got some tests where he was doing that. He'd go under the overpass on the freeway, and you'd see it drop out, and then he'd say he'd note, here's how long it takes to come back on. And I don't know if we ever went through a long tunnel or not. We've got a tunnel downtown Minneapolis. It's a big long one. That definitely will make it drop out. So I could stick it on my car and drive through there and see what it does. And just driving to there, either from my house or from work, and just watch the whole path and see, you know, does it stay locked on the whole time, except when I go under a bridge or go through the tunnel or whatever. That would be something else important to know. And I don't know about that. There's a section of trees that I would drive through when I drive over to Jimmy John's, that for some reason when I go through the trees, it would drop out. And even during the winter, when there's no leaves on the trees, it seemed to be dropping out. But then I got to the point where even my L1 band only U blocks, I got to the point where I could drive all the way over there and back, and it wouldn't drop out at all. So this stuff just confuses me. You know, you look at it, and some days it works, and some days it doesn't. So
Yeah. You can stick a large metal salad bowl over your GPS antenna if you want to simulate a tunnel.
yeah, that would work. Well, I can't do it on the one that's up on the roof, so
That's a little hard.
I could probably just pull the cable out too. I don't know if that's valid to do that or not, but I'm sure that would do it.
You're going to need to put in your budget another robot so you can drop a salad bowl over the GPS antenna on the roof.
Yeah. So I guess I don't have anything else.
That's good. It's interesting. Al is going to make a comment. Al's going to be our benchmark.
I don't know about a benchmark. I think I'm more like the slow one in the group, but
You're smart, like the ducks that fly in the back of the pack. Just smart.
well, when Jeff said he only got it painted, I told myself some days if I could just get one screw implemented every day, then I'm making progress. So every little bit helps. Matt, can I just quickly share what I was working on?
Totally.
Let's see, turn on share. So what you're seeing here is my laptop sitting on top of the motor of the lawn tractor, and this is what Jeff and Matt and I call the half moon gear, which is the steering gear. Here's the steering shaft. These are the rods going out to the wheels. Matt's got his analog steer angle sensor connected to this spur gear, and I was taking just a slightly different approach and have got I think they call it a magnetic rotation sensor mounted here. This brass rod, you can't see it, but at the top of that brass rod is a magnet. You see my screen, just to confirm?
Yes.
Okay, cool. I mean, and then the physics of it is because I've previously printed this, when this gear turns, this magnet rotates, and the sensor in that is able to detect that rotation. And in a very crude test, and again, this is the OEM software that is provided. At one time it's 360 degrees, and at the other extreme it's like 51 degrees, I think, or 100 and anyway. Bottom line is we're getting about 100 degrees of rotation, which translates into more than likely about 1,200, somewhere between 1,200 and 1,400 ticks. Matt, in his analog devices, you know, the one extreme is, I think, Matt, you said 200, and the other extreme is 800, or he's getting, you know, effectively 600 points of measure. So if we can make this magnetic deal robust, and by robust I mean able to handle vibration and whatnot, then, you know, the opportunity is that it'd give more resolution, which hopefully would in turn translate into tighter steering control. So the next step is to get this connected to the RPi and get it connected to the Teamsy, and getting the data going into the Teamsy and able to feed that into the RPi. So now it's back to the electronics side of our, or I'm sorry, the software side of our task. That's where I'm at.
Were you planning to connect that board to your Teensy or to your RPi?
The way I was going to follow Matt's lead, and so he's feeding this signal into his Teensy.
Okay, because in order to do closed loop steering, you want to feed that into the Teensy, and then it controls the steering motor, so it can all do that independently of the RPi. So I didn't know if you said something about getting it into the RPi. I didn't know if you're trying to connect it directly to that, but I think the Teensy is where you want to go with that.
Yeah, so into the Teensy, but I want to program the Teensy through the RPi using Platform IO. So I'm not having to, you know, plug the Teensy in every time I want to change some configuration setting on the Teensy. So that's really the software challenge, to make that all work. Matt's figured it out, so I just need to sort of follow his lead.
That looks really nice.
By the way, the other day you mentioned you were playing with that program from Matt, and your computer would not boot up the next day. Did you get that fixed?
Yeah, thanks for asking. I did not. I have one dead computer now, so and it's asking for, well, what is it? What was my problem? I was trying to go back. I had a cloned image of it that I had saved as a backup, and that seemed to work, but then after it reboots twice, it fails again. So it's a mess. That's where I'm at.
Well, that's very unfortunate that your computer's died on you.
So I've just been using my Windows machine, and I'll try to deal with my Ubuntu machine a little bit later. I'm just going to take it to work and see if the guys at work can figure it out.
That's pretty cool. Your sensor gives you an angle measurement. So you have an estimate of your steer angle.
I mean, it's detecting the rotation of the magnet, so it's effectively saying what what position is the magnet in. It's certainly not giving what position the vehicle is in. It's just purely the magnet, the rotation of the magnet.
I assume that translation is done in his Arduino code that he's got. When he posted that picture, that part was cut off. It just said call the routine to read it. There's a returning angle. So I'm just wondering if there's some magic lines of code that say read the binary data from the sensor and multiply by the scale factor to give you degrees. But
That's what
but either way, he is getting degrees out, so that's handy to know.
Yeah, they take the sensor. I think natively puts out between 0 and 490 or 4095, and they just multiply that result by I think it's like 0.876 or something. And if you do that math, you get to 360 degrees. It gives you a float number, which gives you a perceived level of precision. I'm not sure how that would work in practice.
Just wonder if that would come in handy when you're calibrating your vehicle. Like if you're trying to figure out the curvature, driving your vehicle in a circle and measuring all this stuff out, you would actually have a sensor that could give you an angle.
I guess if you set it, you can program these things to, reset the default. Like, I guess you could put the wheels straight and reset it to 0, and so you would know, what angle that's turning left or right. Again, it would be interesting. You'd probably know more about whether you could actually use that or not. Because as you described it, the ROS needs between -1 and +1, right? For the Z angle.
That's what we've been using. That's like on the joystick control. It will send between -1 and 1 for your angular velocity.
Yeah, it might say some calculation about, rate of angles per second or whatever, but the math is try 4095 times 0.0876 and you'll get to I think 358, something like that. Yeah, 358.7.
That's cool.
That'd be where I'm at.
Progress.
A little bit, yeah. It's very cool to see the level of precision that little doodad for. I think it from DigiKey or Mouser is $16.
Nice. Well, Chinmay, do you want to give an update on the perception project?
Yeah, so there's not much updation. So I tried to download the model. Try to download the dataset, but I'm not yet integrated it. So I'm running with the standard Cocoa dataset. So there are not more updates. So by next week or following week, I can give some updates.
Okay. Awesome. Good luck on your internships.
Thank you.
I bet. It's 9 o'clock. Alan, any last questions? You got the thought-provoking questions.
Oh, not for tonight. I guess maybe on your GPS systems, where you're getting centimeter accuracy. Maybe are you getting that for free, or is everybody paying for that?
Go ahead, Jeff.
Was your question the correction data? Do we get it for free? Was that your question?
Right.
It depends what state you live in. Where do you live?
Wisconsin.
You might have a good chance of getting it if you search. Go to the internet and do a Google search for CORS, CORS space correction, and then see if it pops up. And maybe put the name of your state in there and see if it pops up and tells you have it. But we know for a fact Texas does not offer it for free, and Philadelphia does not offer it for free. And since Al is both in Philadelphia and Texas, he's screwed both ways.
Right, very nice.
I'm in Minnesota and I get it for free, and down in Iowa where we have our other Danfoss plant, they get it for free down there.
Okay, very nice.
And it may have to do with the fact that, you know, in states where the entire state is agriculture, that could be that you got a better chance of getting it. So I'm thinking you might be able to get it for free where you're at.
And then just buy a hardware GPS device that'll pick that up and good to go.
Well, there's several pieces to it. So you have to get a GPS receiver, and then you have to have some way to get the correction data. So if you have a cell modem or just a cell phone, you could actually get a cell phone and connect that to your GPS. There's a guy, Lefebvre, Lefubre or something like that. He's got software you put on your cell phone that will connect to your local DOT and get the data from the internet and put it out the host port on your cell phone, and you can use that to put the correction data into it. So there's a couple of pieces you need to make it actually work.
All right, very good.
The new receiver we're using now will run you around $200 depending where you buy it from. You can either buy it from somebody in Madrid, Spain, which is where I got mine, and the one that Matt has right now. That's where those came from. SparkFun has a version of it. There's a new one that just came out, Drotech, I think it's called. They just announced they've got one for $200. That's the same chip on a board and it's about $200. And there's two or three of them out there, and I can't remember who the other ones are. But it's the new. I don't know if you follow GPS or not, but a couple of years ago, SwiftNav came out with a Kickstarter saying we're going to build a GPS that's a multi-band receiver, which is a big deal because the single band, like I was showing on those graphs, the single band doesn't work as well, and the dual band will lock on faster, and it's just more accurate. So SwiftNav came out with this, and for $2,000 you could buy an eval kit. They gave you 2 receivers and 2 antennas and 2 radios so they can talk back and forth, so you build your own base station. And so for $2,000 or $1,000 per unit, you could get that to work. And now U-Blox, just in the last 6 months or so, came out with this one. It's a dual band receiver, and you can get it on a board for $200. You just have to feed it correction data either from your own base station, which means you need 2 receivers to do that, or you can feed it from your state DOT if they offer the information to you. But you got to get some kind of a cell phone connection or a Wi-Fi connection or some way to get the data to your GPS receiver. And one other point on that, I like to put on the best antenna I can afford, because if you put a crappy antenna on your thing, it's not going to work well. And I haven't decided, exactly. For $100, I can get a survey grade antenna to put on the thing, and it works pretty well. And I've got a couple other things in between that I can try when I get some time to play with it.
Okay, well, that's awesome. Thank you for that input. I'll probably follow up later.
And Al just bought some from China and got screwed by the import tariffs. So you got to be careful doing that. But he's paid a lot of money for his, so it was a big bite when they said, "Oh, you got to pay 25%." So
I don't consider I got screwed. I think I was just contributing to the trade war between the U.S. and China.
Well, yes, I guess you can look at it that way.
Good. All right. That's great seeing everybody tonight. Hope you guys have a fun week.
Thank you.
Thanks, Matt. Thanks all.
Have a great night.
You guys.
Bye.
Okay, bye.
All right.